Okay, so like I said, the Q component family allows you to manipulate strings of entries. When we talk about strings of entries, we're talking about strings of elements, not like Java strings or, not Java strings. We're talking about mathematical strings. So strings could be pretty much anything like other strings. You could have a string of strings. You could have a string of integers. You could have a string of XML trees, a string of any basically object that you can reason about in Java. And they are FIFO, yes, first in, first out. Of an arbitrary type. First here refers to the temporal, which just means like time-based order in which entries are put into the string and then taken out, not about the left to right or right to left order in which the string is written down. Oftentimes, when we talk about stacks, you might see it written as like 4, 5, 7. What refers to as like the top of the stack or the bottom of the stack is pretty irrelevant. The only thing that matters is that the first thing that's added to the stack, or the last thing that's added to the stack, is the first thing that's removed from the stack. And Q is the opposite. Here's that image that I said would be seared into your brain. It's probably beginning to get there. You have the standard interface, which is at the top, which contains 3 methods: clear, new instance, and transfer from. Then, like natural number, you have a kernel interface, which defines the minimum viable product for all Qs that could exist. And then you have, extending from that, another interface, Q, which will contain a bunch of other methods that will help you reason about and work with Qs in Java, but are not necessary in order to implement a Q at the basic level. And then OSU CSE has provided you 2 implementations of Q, Q1L and Q2. This should look very familiar because it's exactly the same as natural number. The only difference is that we've replaced natural number with a Q. And the methods are different, but we'll get into that. Standard has contracts for 3 methods, which are clear, new instance, transfer from. Lock that in. The Q kernel has 3 methods, which are onQ, dequeue, and length. We have weird ways of defining how we add and remove elements from queues and stacks. Queues, we use onQ, dequeue. So onQ would be adding something to the end of a queue. So we're onQing it. And then removing an element from a queue would be dequeuing it. A lot of silent letters. Stack is a little bit also weird. When we put something onto the stack, we say we push it. And then when we remove something from the stack, we say we pop it. We push something onto the stack, we pop it off the stack. General terminology for that. And then length, as you can imagine, will give you the length of the queue, however many elements are in it at the current time. And then we only have 6 additional methods in the generic queue class, which are append, flip, front, replace front, sort, and rotate, all of which we will get into today, all of which are useful methods if you're going to reason about a queue in Java. So talking about this idea, again, of how types in Java, I'm going to erase this, by the way, can be modeled by mathematical types. We say that Q, the Java component, is modeled by a string of T, which is pretty generic and doesn't really get into anything serious, but pretty much all data structures consisting of elements are strings of generic types T. So an array could be modeled as a string of T. A stack could be modeled as a string of T. The mathematical model for all of these is pretty much the same. The thing that differentiates them is how you add or remove elements to them. And then in terms of arrays, there's some other things, like you can have constant lookup time. But for queues, modeled by a string of T. T is what is known as a generic type. So a generic type simply means that it can be anything. It could be a string, a Java string, an integer, a Boolean, a natural number, another queue if you want. So Q is a generic type, or also known as a parameter type. The actual type of the entries is selected only later when the Q is used to declare or instantiate a variable. So with natural number, since natural number was modeled by a different type, it was modeled by this natural thing which we knew what it was. When we declared one, we just had to say natural number. So X is new natural number. 2. With the value of 4. Declaring data structures like we do in OSU CSE looks a little bit different. Still begins with the static type, or the name of the interface on the left, and then in these brackets or less than or equal to, or whatever those symbols are, you define the generic type or the type of value which you want to store within the queue. So in this case, we're saying that we want to have a queue of integers called qi, which is going to be a new queue L, brackets afterwards, right? It's going to be a queue of integers, and then we're going to have parentheses afterwards. In terms of defining queues, there is only one constructor, which is the empty argument. So there's no way to define a queue with already existent elements within it. The only constructor you can do is the empty one. But you could swap this out for, say, like a string, and then it would be a queue of strings. Or you could swap it out for a Boolean, and it would be a queue of Booleans, so on and so forth. But we're going to go back to integers because there's a important note. You might notice that when I'm writing integer here, it is not how we typically write integers. So we have the primitive integer, right, which is int. But we also have these things in Java called wrapper types. So this big integer, or this integer with a capital letter, is called big integer, and it is a reference type because, as will be shown in the next slide, queues can only hold reference type variables. So it cannot hold primitive type variables. And so in order to store these values, integers, booleans, any of the primitive types that we have, Java has these built-in classes called wrapper classes, which basically wrap primitive types in a reference, and we refer to them as big integer or big boolean or big double. And what essentially happens is instead of having, say, an integer x, which contains the value of 4, it does pretty much what we do with all other reference types. It stores a reference to an actual integer of 4. Luckily, since it's baked into Java, you can reason about wrapper classes as if they were normal integers. So with natural number, sometimes you have to print out like toString, or with an XML string, you have to print out toString. But you could basically treat integers, big integers, as a normal integer with printing it out and passing it. And Java will do something called auto boxing and auto unboxing, depending on whether or not it needs the reference type or the object value. And we'll get into this right now, actually. Formal parameter type. Here, the actual type or the argument type is integer. So we have the formal type is a parameter t, which is generic and take on the form of many different things. The actual type in this case is an integer. And saving yourself 7 characters, Java can actually infer what you're trying to store just based on the static type over here. So you don't even need to include both integers. If you include just that, it will infer based on the fact that you defined it as an integer over here that you want to store integers. So technically, you just need this as declaring a queue, which is going to store integers. Okay, wrapper types. So we use big integer and not little integer here. Java commands that generic arguments must be reference types. So natural number, XML tree, so on and so forth. Each of the corresponding primitive types has a wrapper type that is a reference type in part to satisfy this. So instead of Boolean, we have Boolean. Instead of car, we have character. They're just big versions of the primitive types. And they're called big integer, big Boolean, big character. Each wrapper type is an immutable type, meaning that it cannot be changed, like how most immutable types cannot be. There's a constructor from the corresponding primitive type. So if you wanted to make a big integer, you basically just say integer I equals new integer 4, and that will make an integer reference type I. Java includes features auto boxing and auto unboxing, so wrapper types can be used with primitive type syntax almost as if they were actually primitive types. So you might actually be able to just skip this entirely and just create a big integer by doing this. And it'll be a reference type integer, big integer, as opposed to a primitive type. Okay, that's generics and like big integer and wrapper types and that kind of thing. Essentially, you can treat them exactly as if they were primitive types, except they're not. They're reference types. So you could store them in data structures like queues and stacks and sets and sequences are the two other ones that we'll talk about. Questions on that? Okay, back to queues. Like I said, there's only one constructor for a queue, which is the empty constructor, and just creates an empty queue that you can then on queue, dequeue, do whatever you want to do with the queues. So I think there's a tracing table next here. The contract essentially says that this is an empty string because, as we talked about, queues store strings of values. So if we say q, qi equals new q1l, essentially what we're saying is give me an empty queue. So all the methods that we're going to be talking about, there's 9 of them, are instance methods. So you call them on an instance of a queue. So queue dot method name, and then pass any arguments into that method name that you have. The queue must be initialized. Yeah, that's base requirement. All right, first one, on queue adds X at the back or the right end of this. Another thing to note is that since we're working with reference types, everything will be aliased. So in the contract, they will specify what is aliased. So in this case, we're saying that an alias is a reference X. It updates this and ensures that this is equal to the old value of this, concatenated with the value of X. Since it's a reference type, I'm going to, again, implore you to draw pictures if you are asked a question about reference types on an exam, because it makes things so much easier to reason about and figure out what's going on. So the list of references that might be aliases upon return from the method is advertised here because aliasing is important and otherwise is not specified. So this is not a big deal for immutable types, which cannot be changed like the wrapper types. But say you had a queue of natural numbers, then you could get into some pretty dangerous territory where you have a reference to a natural number, and that natural number is also contained within a queue. And then if you update the natural number, it also gets updated in the queue, which would have bad consequences. So I'm going to practice what I preach and talk about what this looks like. If you were asked, what is the resulting value of on queuing 70 to a queue of 49 and 3? Here's what the queue looks like. You have a big queue, which is pointed to by qi. And it has 2 values, 49 and 3, which are reference types pointing to integers of 49 and 3. And then we have a lonesome big integer over here, 70, which is outside of it. And then we call q.onQk, which creates an alias to X. And so we say that we now have another entry within the queue, which is alias towards 70, sorry. And so afterwards, you can see the queue that we have is 49, 3, and 70. So this is what it looks like before. My laptop just almost died. We have qi, which is pointing towards a queue, which has a bunch of reference types to 49, 3. And then afterwards, we have an alias that also points towards this big integer 70. So you can see how if these were natural numbers, it could get confusing, because if you modify whatever the alias is at the back of the queue, it's going to update that k. If you change that value of k, it's also going to change the value of the last element in the queue. So when we're talking about tracing tables, if we had 2 things that were alias before, we had the arrows, but there's not really a good way to do that. You could technically have an arrow that points here and then draw an arrow over there. But that's kind of difficult to do, so we will not do that. That's why you should draw pictures. Again, I will implore you to do so, but half of you will not listen to me. Since integer is immutable, there is no consequence because there's no way to actually change the value of big integer after it's been defined. It is immutable. But like I said, consider these were natural numbers, then there would be consequences. That is a form of dangerous aliasing. Questions? All right, first one down. Next up is dequeue, which removes and returns the entry at the front or the left end of the queue, because the first element that has gotten added to the queue is also the first one to be removed. It requires that there's actually an element within the queue, and it ensures that the old value of this is equal to the value that has been dequeued, concatenated with the new value of this after the element has been dequeued. So again, we have, it looks like the same exact picture, 49, 3, and 70, and then K is now not pointing towards 70, but K is pointing towards a new integer of value negative 554. So what's going to happen when we call dequeue is that we are going to remove the alias of the first element. So it looks like 49. We're going to store it in this alias of K. Instead of pointing towards negative 584, K is going to point towards whatever the first element in the queue is, and then this reference will get deleted. So now the queue stands at 3 and 70. And K is equal to the value of whatever was returned by the dequeue method. So afterwards, we have 3 and 70 contained within the queue, and then K is pointing towards that 49 value. And there's no picture. Finally, the last method that is in the kernel class is the length method, which just returns how many references or how many triangles are stored within the queue. So if we have a queue which has 3 elements in it, and then we set n equal to qi.length. Who can tell me what the value of n will be if the queue has 3 elements in it? Starts with a QHR. Anyone? Yeah. 3. Good job. All right. So yes, if you call an element, if you call length on a queue of 3 elements, the length will be 3. Not a trick question. It's 3. Okay. Front returns. Okay, so that's all of the kernel methods. So all of like the base implementation of a queue. That's anything you could do or want to do with a queue could be done with onQ, dequeue, and length, essentially. Now we get into the extraneous methods that are not necessarily required, but are helpful. So tFront returns the entry at the front or the left end of this. It is an alias or a reference to the front, but it does not remove the value that is at the front. So essentially, it's a way to look at whatever the first value is. If, say, you want to check it before you remove it. Yeah, so it doesn't remove something, but it returns an alias to the front. So 49, we're back in the queue. Okay, we're just pointing towards 58. That's a square. So this is the value of our queue. And then we're saying that K is going to equal to the qi.front. So whatever the first element is, that is what K should point towards. So now alias to the front object, which is our value of 49. So it should be 49 afterwards. Yep. And these two things are aliased. This K equal 49 and the first element of the queue are aliased. Not shown in the tracing table, but shown on the picture. Not important for immutable types like big integer, big character. Very important for mutable types like natural number. Questions on front? Oh, there is a picture. Nice. So there's the before, and then afterwards we have an alias to this first element. And then 58 will get destroyed by Java's garbage collector. Okay, replace front replaces the front of this, so the front of the queue, with X and returns the old front. So it creates an alias to the reference X. It updates this, and then this ensures clause, which is a monster of an ensures clause. Replace front is prefix of the old value of this, and the new value of this is equal to whatever was replaced with the old value of this past the first element, which is a lot easier to see in pictorial form. So let's see what that looks like. We have 49 and 70 stored within the queue. So this one is gone. Goodbye. And then we're saying that K is equal to the integer negative 58. And then we're saying that J is equal to 16. Little j. 7. when we call K, we're saying that K should be whatever is returned by whatever the old front is. So K should be equal to 49. It's the old front. And then we're saying replace that old front with whatever J is. So this reference right here should be J. And now that J is aliased to both that value of 16 as well as the first value of the Q. So we've replaced the front element of the Q with 16, and 49 has been stored in K, which is a returning value. So we have first element of the Q is 16, second element of the Q is 70. That's right. K is pointing towards 49, which is the old value of the front. And then J is pointing towards 16, which is aliased with that first value of the Q. This one's a little bit, this is what I would definitely recommend drawing a picture for. Well, I recommend drawing a picture for all of them, but this one can get pretty hairy. Another way that you could use, oh, well, here's another image with better drawn pictures, but afterwards, yeah, the aliases can get, this is why aliasing is confusing, because sometimes it can get very annoying. So draw pictures, draw pictures, draw pictures, draw pictures. Another example, another way that you could use replace front is by basically swapping out values. So if we go back to our old picture where this Q is just getting, J is pointing towards 16. There is no K. We've destroyed it. And the first value of the Q is once again 49. Here we're saying, hey, put 16 at the front of the Q, and then put J, the old value of the reference, to the old value of the Q. What this does is it just swaps whatever the value in J is with the front of the Q. So what will happen is A, U will come over here, and then U will come over here. And it'll swap the values. So now the Q will be 16 and 70, and then J will be 49. You're just swapping the fronts. It's a good way to swap the fronts. Because since you can only add to the Q from the back and remove from the front, sometimes it gets a little bit messy if you're trying to, if you want to just basically replace whatever the front element is, the alternative to using the replace front method would be to DQ everything in the Q and then add what you want at the front, which is pedantic. So this way just lets you do that easily. This use of the method avoids creating an alias. It swaps J with the entry previous at the front. So J becomes whatever was stored in the front, and then the first element of the Q is whatever J was. Does that make sense? Awesome. Okay, append is a way to concatenate an entirely other Q onto the end of this. So if you have two Qs, say one has 1, 2, 3, the other has 4, 5, 6, and then you call Q1.append Q2, it will just add all of the references from the second Q into the first Q. So it ensures that this is equal to the old value of this concatenated with the old value of Q. Another thing to note is that it clears Q. So afterwards, the Q that you're appending onto the original Q or the first Q will be destroyed or devoid of any elements. So if we have 4, 3, 2, and then 1, 0 in Q2, afterwards, what will happen is that Q1 will now have all of the values, Q2 will get cleared. Cool. Flip reverses or flips this, essentially just takes all the elements and then spins it around. So if you have 18, 6, and 74, the result of that will be 74, 6, and 18. It's a void method, so it doesn't return anything, doesn't take any arguments, just flips the values. That's flip. Okay, sort is actually something we'll get into. So sort takes in what is known as a comparator. And you can see that the comparator is of generic type called order. It sorts this according to the order provided by the compare method from order. Comparators are something in Java which allows you to define how things should be ordered based on a generic type. So let me say it again in a better way. But comparators allow you to define how things should be ordered depending on what the value is. So usually you will never have to make your own comparator. But there are different comparators that exist. So if you have a comparator of strings, so instead of a comparator of T, which is the generic type, you have a comparator of strings called order. This order comparator will define how strings should be ordered. So should values that come earlier in the alphabet be sorted less than, equal to, or greater than values that come after the alphabet? In terms of natural numbers, it would be less than, equal to, or greater than. What it ensures is that the old value of this is ordered by the relation computed by order.compare. So order has to have a method called compare, which takes in two reference types and returns -1 if the first one is less than, 0 if the first one is equal to, and 1 if the first one is greater than the second element that's passed in. And there's an example of a comparator on the next slide. So this is what a interface comparator looks like. So the contract returns a negative integer, 0, or a positive integer as the first argument is less than, equal to, or greater than the second one. This is like the string compare to method or the natural number compare to method, which takes in two objects or generic types in this case and returns -1, 0, or 1, depending on the ordering of them. The notion of less than and greater than is quite flexible. The notion of equal to is not flexible. It is based on mathematical equality, not on a flexible notion of being equivalent to. So what we mean is when we're talking about less than, equal to, or greater than, you always want to be reasoning about the mathematical type. So if two natural numbers are defined and they don't have the same, or I'll just draw an example. So if you have two natural numbers and they both contain the value of 0, use equals equals in this case, it'll compare the reference types, which will not be equal. But what we're actually worried about is the mathematical type, which is these mathematical types of 0. And these things are equal to each other. So a comparator would have to make sure that that returns 0, indicating that they're equal to each other. The meaning of a total preorder means that for any two values of type T, the generic type, they have to be comparable and there are no cycles. So A cannot be less than B, which is less than C, which is less than A. Here's an example of a comparator. It's essentially just an integer comparator, which returns -1 if O1 is less than O2, 1 if O1 is greater than O2, and then 0 otherwise. Let's say that you wanted to make a comparator that was the opposite. So greater numbers came first. You would simply just reverse this. And then you could pass that comparator into the sort method, and it would sort the queue based on that total preorder. Let's say that you wanted to make a comparator that just put 42 at the front and then was just normal for everything else. Well, you just add an additional check that if the value of O1 was 42, it would be first and would return 1. Otherwise, it would return whatever this is. And then if you called sort with the comparator passing into the sort method being that weird funky comparator, and then you had a value of 42, it would go towards the front. People get tripped up on comparators and like, will I have to implement a comparator? No, you will not. You will not have to make your own comparator. You will just have to know what they do, which is define a preorder or an order of elements. And once you have a comparator, you can pass it into the sort method, and it will sort the queue based on that preorder. A class that implements a comparator, you'll see that it implements this comparator class, which is the interface that's defined up here. It's usually a nested class. So if you're defining like a natural number 1L class, I think the natural number 1L class has a comparator within it because it needs to define how natural numbers should be compared against each other. So it should be declared as private and static. Now, essentially, you're overriding the compare method that is in the comparator interface so that you can provide your own implementation of how things should be ordered based on those reference types. An easy comparator is to just use O1.compare to O2, which will just default to like the compare to method that's built into Java. And this essentially will do the same thing as this comparator up here, which just returns depending on their order. Any questions on comparators? Cool. So If we have a comparator of integers, which is a comparator of integers, which is a new integer less than, which is this comparator that we defined up here, which defines integers that are less than integers. Okay, which defines that smaller integers should be less than, equal integers should be equal, and greater integers should be greater than. And then we use qi.sort. We pass this comparator in. We're saying sort this q based on the comparator where smaller numbers come first. And then afterwards, the q will be sorted like that. Okay. Rotate will rotate the q by a certain number of values. So it rotates this, it updates this, and then I'm not going to go into this contract because that's behemoth. But it rotates to the right, I believe. So after rotates to the left. So afterwards, any value, you'll just move it that many spaces to the left. And then once it gets to the front, it goes to the back again. So if we have 8, 6, 92, and 3, then we rotate it by 1. 6 will move up to the front, 92, 3, 8. We do the same thing, but we call qi.rotate 3. 92 will be moved to the back because it moves 1, 2, 3 spaces, so on and so forth. And then you can do negative numbers if you want to go the other way, where 3 will now be moved to the front, and then all the other will be maintained in the same order. And that's Qs. Big thing is first in, last out. First in, first out, FIFO. First in, first out, FIFO. It's like a queue. It's like a line at an amusement park. That's what I think about. Draw pictures, especially when you're reasoning about using the instance methods and the aliases. They only take reference types. And then also that aside that you can't store primitive types. You have to use big integer, big Boolean, big character. That's all I have in terms of lecture material. So you can head out if you want. Otherwise, I'll take questions about the midterm. If anyone wants to ask questions about the midterm. Yeah. Am I what? I can. I can do that. Tomorrow at like 6, if that's okay. And I'll record it and I'll upload it to YouTube. Tomorrow at 6 p.m. 6 p.m. to 7 p.m. I will do a midterm review on Zoom. It'll be my office hour Zoom. Yes, please come with questions. Otherwise, there is no sample midterm 2 that's posted publicly. You can get one from the test bank, but I don't think I can go over that one. So I'll just yap again if there is no questions. But yeah,
allowed to go over those with us?
I don't think so because it's weird. I asked Bucci if I could like bring it up, and he's like, technically, because they're not like public and you have to request it. It's like COAM if you send it, which is stupid. Well, I'm not gonna say so.
Is the rest of the other computer science classes are not like that, correct? Like this one is overseen more so than the other ones, or am I mistaken?
No, they're all pretty much the same, but all the other CS classes have materials on the test bank.
Okay.
I think in terms of like you have to take software 1, and then that goes into software 2, and then you have to take foundations 1, and that goes into foundations 2, and you have to take systems 1, and that goes into systems 2. All 6 of these classes, I think, have materials. Okay, and this is like the base game of OSU CSD. And then you can, what's up?
For like the projects for these, those are all like made by Bucci and they all have the same.
So software 1 and 2 is like Bucci's domain.
Okay.
Foundations 1 and 2, there's a bunch of professors. Some of them have projects, some of them don't. I didn't have a professor that made me do projects for Foundations 1 and 2. Pro tip, these are just math classes, but disguised as CS classes. And there's also a secret 3rd version of 1, which I failed. But I don't think I'm going to fail it again. We'll see. And then systems 1 and 2. Those ones are the worst ones that you have to take. Yeah, they're bad. Systems 2 is a lot. Systems 1 is a lot because you're learning C and then you learn assembly. Foundations 1 and 2 is like all like math, like asymptotic notation. So what makes an algorithm like good? How do you analyze it? And then what are like graphs and graph theory and all that. Systems 1 and 2, you learn C and assembly. And then this is all Java. And then you get into yeah, there was. I'll pull it up.
And you thought systems was the hardest?
Systems is by far, I think, the hardest and the most, I'm not gonna say boring, but difficult to sit through. It's very interesting. I'll say foundations 1 and 2 are probably my favorite classes. And then you get into the project classes, so you have to take 3901, which is like web dev. You have to take 3902, which is like game dev, which is fun. That's the one I took. And they used to offer a 3903, which was like you built your own compiler, but I don't think they offer that anymore.
Okay.
Yeah, there's the like roadmap for CS classes is so confusing. And unless you like sit down with your advisor and like go through it or like pour over the syllabi for a bunch of them, it's kind of hard to know what you have.
I think
to
even
take.
then it's kind of confusing. Like
It's like take this, take one of this, or take
yeah.
a total of 6 credit hours from like this or this. It's rough. A lot of fun classes though. Of
Cool. Thank you.
Yeah.
Appreciate it.
course. Yeah.
So say I alias, like say I have a natural number N1 equals 4 or something.
Okay.
And then I'm gonna draw it.
Draw pictures.
And then I alias N2 to N1. Would I have N2 point to N1's reference value or object value?
So you're saying like if you did N2 equals N1?
Yes.
What that does, you could draw either one, like N2 point towards N1, or you could point towards N2 to N1. The result is the same. If you tried to print out N2, Java follows the references until you get to an object.
See, that's what I was thinking, but when I was at the midterm reviews, the dude pretty much said I don't point at the reference value. And I was.
Well, yeah, that's because aliasing with mutable types is very dangerous. It's just like generally considered not a good idea to alias guys.
I know that was like one of the problems though. We was going, they were passing numbers into a method and then like they were getting alias to each other and then they said like draw like the result.
Oh, I see. Okay, yeah. So for like parameter passing,
Yes.
so if you have like foo, what was it like natural number 1 or natural number like N1 and N2?
Yeah.
And then you had say like, I'm just gonna say like X4, Y 5. When you alias, those values get pointed towards the object values.
Okay.
So N1 points towards that, N2 points towards that. So anytime you call like an instance method that goes to like update this, that's also gonna update outside. But if you said like N1 equals new natural number 2, like 42.
Now I have a new value.
What that does is now N1 is no longer gonna point towards this object value. Got a separate natural number.
So even though they're passed into the same parameters, they're not the
Yes.
same thing.
They're pointed towards, I would say always point towards like the object values.
Okay.
That makes sense. But if you call like N2 dot increment, now you're updating the object value of Y. It's supposed to be Y. So now this becomes 6, and then outside the method, Y is now 6.
Okay.
But if you reset the reference values of like N1 and N2, now you're saying, hey, no longer point towards those variables that were passed in. It's like an entirely separate thing. That's why that divide question was 8 and 5, or whatever you thought was.
All right. Thank you.
Yeah.
So for the process,
Yeah.
the grader told me like it doesn't pass its test, but then when I run it again, pass it. Actually, before I believe in Kansas.
Can you send me a message on Carmen and then I'll download the zip file and I'll run it and I'll make sure.
Do you want me to send you this zip file as well?
No, because I can just go to your submission to download it. Okay.
You remember this example from class?
Yes.
Doesn't J like reference 2 values in one line? Is that fine?
Yes, because what you're doing is you're just swapping the aliases. I can see what you mean where. So wait, the Q is pointing towards, what values are in the Q?
49 and 70. And then J 16.
So what happens essentially is you take the front and you point it at whatever is passed into dot replace front, which is this value pointing at J. Okay. And then you point J towards whatever value was at the old front. So J is being both the object value of J. Okay, actually, here's a good way to think about it, is that the object value of J is getting replaced at the front. The reference value of J is getting pointed towards the object value that used to be.
But I feel like if we did something like this with natural number, I guess, like, wouldn't it be bad practice?
No, because there's nothing being released. Like there's nothing being pointed to by two reference variables. If that makes sense. Okay. I think the first example, wait, go back up to the picture on the first example. But yeah, there. This case, there would be a harmful alias because that value of J is pointing towards 16, as well as that value within the Q is pointing towards 16. Okay. Anywhere where you have two reference values pointing towards one object value, you have harmful alias. Okay. Because anytime you update that object value, it's going to update it for the other reference variable. Okay. Make sense?
Yeah, that makes sense.
Okay.
Thank you. Oh, what would you recommend us like looking over the help study or like redoing?
I would say the biggest thing that people trip up on is what I just went over with Kaden, which is like passing values into methods or like functions. And what happens, like drawing pictures is just the biggest way to just like make sure you're doing the right thing. So make sure you understand that. With strings as well, go over some string examples of passing strings into methods. And then make sure you can write recursive methods is what I'd say.
Thank you.
Yep.
Thank you. Are we also not fixing tables on the?
Yes. My other question was, do I get time and a half for the FLDS thing? Did I have to request that in advance? I don't know.
Let me double check and I'll get back to you on that. I think you can, yeah. There's a class in here afterwards. Let me think on that, ask Bucci, and then I'll get back to you. Cool.